Well, thanks very much. I had a very good time talking with several of you this morning and in the afternoon. And so what I thought today to do is tell you a little bit about the things that I've been doing for a while of modeling the large-scale clustering of the clustering on very large scales, and tell you about some of the progress that we have made and some of the applications that we have used these techniques for in the last few years. So to give you a motivation of why we started doing this some time ago, there are still many open questions in cosmology, neutrino masses, dark energy, etc. And we expect to get answers to at least some of these questions from studying the clustering of matter on large scales. And these are scales where the dynamics is relatively simple, linear theory looks pretty good, but there are small corrections to these linear theory calculations. And for the purpose of this talk, the point is that those corrections, however, the measurements are so precise that those corrections are large compared to the observational errors that we have and that we expect in the future as well. So, it looked like a good place to try to make some progress, not in a numerical way, but more in an analytical way, to try to understand if how we could characterize these small corrections, given that it's a small, they are not so, they're small, and see if we could have control enough to make predictions, what it would require to make predictions comparable to those error bars. And I guess some a bigger picture question would be, what is the actual theory that describes the dynamics on these very large scales, and that would allow you to compute consistently these small corrections consistently and accurately, and to what extent the small scale dynamics that we know is complicated as you zoom in and look at what happens at the scale, say less than 10 megaparsecs, or even inside halos and so on, to what extent that complication affects the theory for the large scales. How is that supposed to be taken into account? Normally we do have a wide range in our everyday physics. We always have theories that describe things on large scales and forget a little bit about what's happening in detail. Maybe we have hydrodynamics and the small scales are only incorporated in some transport coefficients, things like that. How does that work for the large scales of the universe? And so this field of trying to make predictions for the long wavelength dynamics in the universe has a very long history. We can go back to work by Jim Peebles long time ago and many people. But I think in the recent years there has been we've been able to make some progress in understanding what this theory is about, and understanding how the small corrections for the corrections from the small scale dynamics, how do they enter? I think so I want to tell you a little bit about that. So just for concreteness, if you look at the very large scales of the universe, then it looks very simple, very linear. But as you zoom in, the story becomes more and more complicated. And of course, I don't have to tell the audience here, which are experts in trying to understand the small scales and modeling them in computational ways, etc., that as you go in, it's more and more complicated, and those things matter at some level, even as you zoom in on large scales. But if we wanted to ignore that complication, not really ignore, but you wanted to include it in the dynamics on large scales, what do we need to do? And for the purpose, so I will talk a little bit about that, and I will also, using those techniques that we have developed, we applied it to some analysis of some existing data. So I'll tell you about results of that, just to keep saying something that might be interesting to different audiences. So I mean, I suppose most of us that took some cosmology class in grad school or whatever, we know exactly what we need to do if we wanted to do something on the very large scales. Let's say for simplicity here, we're talking about just one, the dark matter only, just for the purpose of this slide. You would say, I write some equations of continuity of mass conservation, momentum conservation, the Poisson equation, and if we are on very large scales, we linearize those equations and we solve them, and that's the end of the story. And that's correct. And the question for the question that we've been trying to making progress solving is trying to see what we do when we want to make not just the linear theory corrections, the linear theory calculations, but calculate what comes after linear theory. What are the small corrections after that? And we know that, for example, if we were to on small scales, things are moving around. There's some random motions due to the clustering of matter on small scales. So even if you just think about naively, you would say, oh, these small corrections would lead to some sort of transport coefficient, some sort of stress energy tensor from the small scales, which is denoted here, tau ij. When we do the linear theory calculation, usually we just put that to 0. We think we are doing dark matter. So this cold and there's no random motions, but that's not the dynamics is generating them on small scales, but or 10 megaparsec type scales, just to say some number. So that is where the effects on the small scales are going to kick in and are important to describe the dynamics even on the largest scale. So now usually one starts by linearizing this equation and having a linear solution. Maybe you have we usually do something more complicated than this. We have dark matter, baryons, photons together in some sort of Boltzmann code, but the idea is the same. And then if we wanted to get some the corrections to that, we would plug into the quadratic terms the linear solution and solve it again and so on. But the point that when we are taught this, we are not usually told is that those corrections have some problems because this theory is not describing what's happening on the small scales, and these couplings mix scales. So when we do this, the small corrections that we are computing receive corrections from scales that we are not tracking correctly with this theory. So those things that we call the small corrections are not really self-consistently calculated unless we take into account somehow the effects on the small scales, which are not described by this theory, we don't know what they are. So somehow somebody needs to tell us from somewhere else, or we need to have some free parameters in order to have even this calculation of the first corrections to this to be self-consistent even mathematically. So so part of the effort that we have done in the last few years to try to classify all of that, try to understand what are the things, where the effects on the small scales are coming in, to what order, etc. And also the realization that there's not just some single expansion parameter there. There's, in this theory, there are more than one. I mean, people know about this already from the smoothing of the BAO scales that people have recognized. But so there's various things that are not so obvious from this dynamical system. So this perturbation theory is a very old school approach. It looks like very from some other era. However, I think this particular area is a place where these kind of calculations are useful because as I will discuss, we will see in the examples, we are talking of a regime in which we are getting the constraints when this perturbative expansion makes quite a lot of sense, and it allows you to, in terms of the size of the corrections that we have to keep track of. And so, spent quite a bit of time trying to make sure that we are doing this consistently, that we understand the errors that we are making, and that even before comparing to any simulations or anything, we can say, what is it that we need to compute, up to what order, what parameters need to be added to the usual calculation to include the effect of the small scales, if we want to have an error bar of a given size, and then developing techniques to do this even analytical calculation fast enough that you can put them into an MCMC and fit for parameters. So that's what we have been doing in the last few years. So as an application, so I will do it a little bit the opposite order. I'll tell you a little bit about one application that we've used that we've done in the near past, and then I will go back and tell you a little bit about this theory. So one in this application, we fitted the clustering measurements from the BOSS survey, and by also considering by using these techniques, we were able to extract constraints on parameters, and I want to highlight a constraint on the Hubble parameter. So most of you, I'm pretty sure, and the cosmologists in the audience know about the BOSS survey, probably more than I do. The goal of this survey and others was to measure in detail the so-called baryonic acoustic oscillations. So the oscillations in the 2-point function of the clustering of galaxies. In the right-hand plot, you can see the 2-point correlation function in position space, and there is this bump around 100 megaparsecs, which is what we're discussing, this baryon acoustic peak. And it's the equivalent of the wiggles in the CMB power spectrum, but in the galaxy clustering power spectrum. The left plot shows the same, but in Fourier space. And so the idea of these surveys was to measure this scale in the matter clustering. This scale can be computed from first principles if you believe in the cosmological model. In lambda CDM, you can compute it from first principle, provided you know the matter content of the universe, omega matter, omega dark, omega matter, omega baryons, which you can get from the CMB. So you can measure from the CMB those parameters. You can compute what is expected to be the standard ruler. Then you see how you see it on the sky and along the line of sight, and then you constrain the Hubble parameter and the angular diameter distance. And that's the goal of the survey, and it's very successful, and everything is great. The little twist that we did was not just to focus on the baryonic acoustic oscillations, but use the entire shape of the 2-point correlation function or the power spectrum in Fourier space to obtain independent measurements of using that shape of the matter density, and thus not needing the CMB as a calibration of the BAO standard ruler. So the 2-point function, the power spectrum of the galaxies in the BOSS survey, I'm plotting here because these observations are not in real space, but what we call redshift space. So peculiar velocities distort the position of things along the line of sight. This 2-point correlation function is not isotropic, and cosmologists typically expand this in multiple moments, and the 2 lowest ones are plotted here. But for the purpose, it doesn't really, for the purpose of what I'm going to say, that's not so important. But you can see that there is some measurements of the power spectrum as a function of the wave number, the Fourier transform of this coordinate transform to the distance. And you can see the wiggles up and down in these curves. Those are the BAO wiggles that were zoomed in the previous plot. But there's a whole shape to this curve that is not just the wiggles, and the wiggles are actually a small effect on top of some broadband shape. And the peak of this power spectrum around K between 0.0 in the plot between 0.05 and zero point 0.1 megaparsecs. That peak that you see, that broadband peak that you see, is determined by the time, the modes that entered the horizon before or after the epoch of matter radiation equality. So they are directly, that scale and the shape of the broadband shape of the spectrum is a direct measurement of the matter content of the universe that is sitting there in the clustering of these galaxies. So we wanted to use that in order to get an independent measurement calibration of the BAO scale, and then use the BAO scale that's also in this data to get a measurement of the Hubble parameter. So basically, the information in this large scale structure, there's various sources of information in that data. There is some distance information from the location of these wiggles along the line of sight or perpendicular to the line of sight. There's also some information in the broadband shape about the composition of the universe, the matter and the baryon density. And in the amplitude, there's also some information in the overall amplitude of the power spectrum that constrains the growth of structure, and people usually want to use that, say, for example, to constrain neutrino masses. For the purpose of this discussion, I'm mainly talking about the constraints that we can get from the broadband shape on the matter content of the universe, on the amount of dark matter in the universe. So there is a measurement also on the baryon density from Big Bang nucleosynthesis that we are going to use. And if we combine the broadband shape that we are measuring in this data to constrain the matter, content, which is called omega matter in these slides, and the Big Bang nucleosynthesis constraints on omega B, one has a prediction for the sound horizon, and then one can look at the position of the BAO peak and get a measurement of Hubble, for example. And in no place did one use the measurements from the CMB itself. And so, yeah, the reason, yeah. So let me get on that in a second. So these predictions from the EFT of large scale structure, this perturbation theory, boils down to some analytical formulas for the shape of this 2-point function, given in terms of integrals of the linear power spectrum of matter fluctuations, with multiplied by functions which we can compute. And but they're normalized sometimes. Some of these shapes, some of these terms have free coefficients in front. Some of those free coefficients come from the relationship, having to model the relationship between matter and galaxies or the tracers in the survey. Other of these coefficients come from the effect on the small scale motions and clustering, even on these large scale dynamics, these terms that were coming in some previous slide from the stress energy tensor. But I'm just flashing this transparency here to say that this is just some simple calculations, some bunch of integrals that one needs to do. They depend on, and in fact, these integrals can be done even analytically. If the power spectrum of initial fluctuations was a power law, all of these integrals have some simple functional form in terms of some gamma function, something you can put in Mathematica. So it's all analytical, and any power spectrum can be expanded as a superposition of some power laws by expanding it in kind of Fourier series, these FFT log techniques that people have developed. So the whole thing is just basically a linear, just a bunch of matrix multiplication. So it's very simple. So there are, however, these free parameters, in this formula, and a few free parameters. This is not a fitting formula, but those free parameters encode, as I just said, the relationship between the tracers and the matter, these so-called bias parameters, some uncertainties regarding the dynamics, that if you did the dynamics in some other way, you might not even have to carry around. And of course the fact that we are tracing the matter density with discrete objects. So we are having galaxy, no galaxy, so that creates some additional source of noise, Poisson type noise. But so just to give a sense and maybe look back into why this perturbative approach makes some sense, at least to me. If we look at the best fit, these are the contributions to the best fit model for the Bose clustering from various terms. The solid black line is just linear theory. And the dots are, if you bin the data in small bins and you get the error bar in each of the bins, that's the size of the error bars. So and the blue line is this first correction above linear theory. Okay, so you can see, and the dashed horizontal line is the noise due to the fact that of the discreteness of the tracers. So the measurements that we are able to make start to become very not very good when the short noise contribution is similar to the power spectrum itself, so around k of 0.2 or so in this plot. And you can see that the nonlinear corrections is only a 10%, roughly speaking, effect. So from the linear theory, the blue line is down, it's around 10% of the total. So in the places where we are getting the cosmological constraints, the universe is almost linear. The corrections are on at the 10% level, roughly speaking. It depends exactly up to what k you go in your analysis. But the error bars are much smaller than that. So if you were, which are the dots, so they are more like a percent at the percent level. So so you are in a regime where you have to be very, so the dynamics is almost linear, but you have to be precise, and that's the reason why I think it's a good place to understand in detail and try to do the things in this way. If we were to compute the next to this leading order correction, you could think that what we call is usually called the two-loop contribution. The ratio between the one loop and the two loop is similar to the ratio between the linear theory and the one loop. And so people have computed this contribution. So at least in some example, in some cases. So it would be similar. That two loop contribution is similar to the size of the error bar. So at the maximum k that we can measure with these surveys, which is around 0.2. So so at least at this level, it looks like you're making measurements in a place where you only need to go a few orders in this perturbation theory to try to get something that is consistent, is precise enough to compare with even with those tiny errors, and that's. And I think we are in this regime, stuck in this regime for quite a while. So I think it's useful to have a good understanding of this regime. Okay, good. So so of course in most situations this large scale structure data is not it's not competitive for constraining many of the cosmological parameters to the CMB. So if you just go ahead and compare most constraints that you get on parameters, say the omega matter H square, things like that, to Planck, you will never make, those constraints would be much tighter. However, in the case of the Hubble constant, so this is not true in cases where for some degeneracy in the CMB data, the constraints are not particularly as good as the statistical constraints might lead you to believe that. And one of these examples is a direct measurement of a constraint on the Hubble parameter. And so and as I'm sure you know, and you are tired of hearing, perhaps there are perhaps a tension between local measurements of the Hubble parameter and the CMB measurements. And so that's the reason why perhaps an independent measurement like this one might be of interest. So here I showed you just the results of doing this fit of the BAO of the BOSS data using this simple model. I mean, there's plenty of I could show you a lot of plots how to test accuracy of the things and blah blah blah. But for the purpose of this talk, let me just boil down to the results. This is just there's, as I was saying, some nuisance parameters, some bias parameters, and so on. We've marginalized over them. I'm not showing them here, but let's focus on the plot for the Hubble parameter. I think you can see first. Let me say again that there are two curves there, or three curves. One of the curves is just the Planck 2018 measurement of the Hubble parameter, or in the context of lambda CDM, I guess, fitting the Planck data to using lambda CDM and extracting what the Hubble parameter is. That's the red line. And superimposed on that, let me just talk about the blue line, which is the result of this analysis, which did not use, so it used the BAO, but it did not use the CMB as calibration of the BAO. So it didn't use any information from the actual experiment, CMB experiment. And you end up with a value of the Hubble parameter, which is very close. It's still in tension with the local measurements, and whose error bar is very comparable. It's similar. So to the Planck measurement. So it's a very small error bars, and still consistent and independent, and also in tension with the local measurement. Now, one thing to keep in mind is that this is in the measurement that is independent from the CMB, any CMB-based measurement or calibration of the BAO scale. However, it is correlated in the sense that it's assuming the same physics, right? So this determination of the Hubble parameter still goes through a calibration of this BAO scale. And if the physics during recombination was any different, then you would end up with a different result in this fit. So it's not that so it's still dependent on the physics during recombination being standard. So if the physics during recombination is standard, then so I'm using the same formulas for connecting the matter density and the baryon density to the sound horizon during recombination, but I'm not using as inputs the measurements from the CMB, but using as inputs the shape measurements that I've obtained from the broadband shape of the clustering of galaxies on large scales from the BOSS survey. So, of course, if you take this tension seriously, you might say perhaps the solution is that the physics during recombination would be changed in such a way that the sound horizon is different. And so when we measure, when you calibrate it using this correct physics, and then you measure the BAO scale locally, you would get agreement with the local measurement of the Hubble parameter. And here, well, let me just advertise, I mean, some work which we did together with Colin, and so you probably know about it, or you can ask him in detail. But one of these examples of changing the physics during recombination to try to reconcile this tension is models in which there's a dark energy component that you have to tune it to be important during recombination. So in the plot on the left, you can see the redshift and the fraction of the energy density in this dark energy component. You need to make it such that it dominates around the redshift of a few thousand, so that it changes the epoch of matter radiation equality, and so it changes, or it changes the age of the universe, so the propagation, how far sound waves could have propagated in the early universe up to recombination, to try to make that shorter, and then as a result being able to get from the same local BAO measurement, infer a different Hubble parameter. So an example of a model that you increase the matter density, or in the form of this dark energy component at these early times, and you are able to fit the CMB data with a higher Hubble constant, is plotted there. And I'm showing this just to advertise the fact that, well, now that we have all of this machinery, we can do the linear theory calculation for this, and then also do the prediction for large-scale structure in the exact same way, consistent way as we did before, and see what happens. Turns out that, so as an example, I'm plotting there, I'm showing there a plot of, so two models that fit the CMB similarly well with different Hubble parameters, one that has this early dark energy, one that does not. And in the plots on the top right, you can see the effect of changing those, adding this energy density on the clustering of galaxies as what would be relevant for the BOSS measurement, even after you've marginalized over these nuisance parameters. Just to say that even if you make the CMB fit, you still expect some changes, residuals on the on the matter clustering at low redshift, because they are sensitive to slightly different. They're sensitive to, in a different way than the CMB, to what the baryons and dark matter are doing, and those effects are small, but they are, fractions of a sigma over many bins of k. And so you might think that if you do this consistent analysis, and this was already there, you would somehow get some hint that this model with this dark energy fits better, but that's not what we found. On the contrary, the constraints on the amount of the fraction of early dark energy at the time of recombination get tighter once you include the BOSS data in addition to Planck, rather than liking to put the early dark energy. So at the moment, I would say that my summary from these measurements is that you get a Hubble parameter which is consistent with what Planck gets, even if you do not use the Planck data itself. You just assume, if you assume lambda CDM and you calibrate the sound horizon from low redshift data, in this particular case from the BOSS survey, you get a consistent Hubble parameter with similar error bars than Planck, so everything seems to be fine. And if you think that perhaps the issue is that both are assuming that the physics during recombination is the standard one, there's nothing funky going on at the time, well, this should maybe leave some imprint in the cluster, even after you fix the CMB to fit Planck as well. There should be some imprint in the clustering on large scales of galaxies, and we didn't see anything there. So anyway, we'll see how this plays out in terms of improved local measurements and other techniques to get error bars and validation of the local measurements, and also the CMB measurements from other experiments, and it will get resolved at some point. But at the moment, it doesn't seem, anyway, that everything seems consistent from this point of view. So so let me go back now to, so I shifted the order perhaps a little bit and told you some application of these techniques that we have been developing to the current data. But I want to go back and tell you a little bit more, at least, about the kind of things that we have been doing. So I want to go back to this plot to again bring back the point that we are in a regime in these clustering measurements in which the universe is, wherever we are getting the information from, the universe is very close to linear theory with small corrections. At the, it depends exactly at what scales you stop, but on the 10% level, just to round it up, and it depends on the redshift, etc. But let me just round it up to a 10%, just to be concrete. Some 10% corrections with error bars, however, that are at the percent level. And so I think it is, if there is a place for this type of techniques, is this one. And also it's important to understand, I think, or to keep in mind that one thing that this brings to the table is that we are able to characterize systematically, how accurate we think our computations are, and where are the effects of up to what order this biased expansion I need to use, etc. Keeping in mind that the errors bars are so small that if we try to make comparisons on small boxes to some hydro simulations and so on, maybe we don't pick up effects that are at the percent or sub-percent level, which are what is important to make sure that, or one has to be careful about making sure that one can pick up these very small effects that are important once we go to these very large volumes of these surveys, but might be more difficult to pick up on small, or you have a small box. And then also it gives you a simple way to marginalize over these uncertainties if you at least have some idea of the sizes of these different coefficients that encode the complications of the small scales, and it tells you exactly how many of these coefficients you would need, etc. So I think it's a useful tool. So so let me go back to this again and tell you, okay, so the idea then, as we all did since our grad school days, or even before, for some probably, you just try to solve these equations perturbatively, and what the goal of the calculation is to get some statistical properties. For example, the 2-point function of the density field, or of the class of the tracers. You can do it in linear theory. You can go to higher order, compute the average after you've solved these equations to some higher order. If you did so, if you solve to some higher order, what you're really doing is imagining that there are some of these Fourier modes that are in the initial conditions. They are interacting through some of these nonlinearities in the dynamics and creating some of the modes that then you're measuring. So, and you're averaging the answer over all these possible modes that are contributing through this nonlinearity to the scales that you are observing. So the higher order you end up with more, you end up with more integrals over all of these modes that are or these stochastic initial conditions that we are solving, averages over the amplitudes of all of these modes that interact and give you what the mode that you are looking for. And so in detail, each of these terms in this expansion for some endpoint function that you're computing end up being a integral over momentum, over the label momentum of all of the small scale modes that you're, or small and large scale modes that you are averaging over. And that's why this is called, it very much looks like a calculation that you do for in field theory for particle physics. It's very similar, but it has some interesting differences with it. But it's again a loop expansion and integrals over momentum, and a lot of the techniques can be borrowed from there, and that's what I mean. This field has a long history. But the important thing is that, or one interesting point is that as you do these integrals in the momentum, you have to keep in mind, you have to remember that this solution that you have done is a good solution on large scales, but on small scales, it's not a good solution. It's not tracking the correct dynamics. This series does not even converge. We think it's an so-called an asymptotic series. So the results of these integrals get contributions from places, because you're doing an integral of all momentum. Each of these loops in these drawings is an integral over momentum, gets contributions from places where you cannot trust the calculation. And so and in fact, just as it happens in field theory, you can easily do examples where you have a power law, not for lambda CDM, but a power law initial conditions, in which when you do this integral, they diverge. And obviously you can run the simulation and there's no problem. So nothing is happening. So it's just a mistake. So clearly, to have this perturbative series make sense and converge, one needs to be a little bit more careful. And the and all of these divergences, and sometimes even interestingly, for example, and there's a paper recently by Leonardo Senatore and collaborators. If you consider two fluids like baryons and dark matter, there's some of these uncertain things from the small scales that are effectively like a dynamical friction that create a force between dark matter and baryons that even enters at the linear scale. At the linear theory, you should have a free coefficient that you shouldn't be able. It's only important for non-adiabatic initial conditions, but there's a lot of subtleties like that that are quite interesting. And it leads to the fact that you have to be sure to model the small scale, include the effects of the small scale dynamics. These small scale dynamics, you can convince yourself that enters in the form of some small number of coefficients, and the structure of those coefficients is such that in examples where you get those divergences or these big errors, they can be absorbed into those in a renormalization type scheme, just like in field theory. So there's a lot of similarities, and you can, if you had some initial conditions, you can compute exactly what the next order terms, you can see exactly what these uncertain, uncalculable terms, I'm calling them the ones that come from the small scales, and they are things that we don't know how to, or we know how to compute up to some overall normalization, this L1 parameter in the equation there that says delta counter term. And we understand the structure, it starts linear, it has a quadratic piece and dot, dot, dot that we could also compute. So there's a lot that you can say and be more or less confident than you're doing the right thing. And if you are worried about it, you can go into simulation and see that indeed you're generating all of these terms, even for dark matter and so on. I mean, of course, for some people doing this, going to the simulation, yes, it's great, but we're just doing a Taylor series. So you don't convince yourself that the Taylor series is the right approach by doing examples. We do examples, but that's not the reason. So anyway, but you can do it, and you can measure these coefficients and get more confident that you're doing things correctly. So, and more importantly, you can have a sense of whenever you stop your calculation at a given order, what is that you left out, how big those things are, how they depend on K. If the universe was simply a power law universe, you can easily write down all of these terms and all of the things that have free coefficients that you don't exactly know what's their K dependence. They're of course all power laws, and you can figure it out very easily. But our universe, fortunately, is not scale invariant, so it's a little bit more complicated than that, but conceptually it's the same. Great. So and yeah, in addition to that, you need to have some freedom for the relationship between tracers and matter, and there's a long literature of many people trying to understand this, how it goes into large scales and how many parameters you need, etc. So let me spend a little bit of time talking about some future things. So I think we can convince ourselves that we understand what's going on with large scale structure. We think we understand how to do calculations that have a given precision, and how many free parameters are needed to encode the small scale dynamic for a given precision, the small scale dynamics that we do not track with this kind of theory. But unfortunately, that is of course the limiting factor at the time of getting constraints. A lot of the constraining power of something like BOSS or future surveys is going into determining those coefficients. And so any progress that one can make in having better priors for those, or having a better understanding and connection to the physics on smaller scales, I think there's where a lot of the improvement can come for us, and by talking to people that work on that part. Of course, we need to do some more higher loop calculations, and also bispectral calculations. And not every calculation we have done, but I think the big elephant in the room is trying to get better priors or predictions for those free coefficients. And so let me give you a sense of that. There's a few plots here from various papers. So on the left plot, you can see there are curves of 3 different colors. Let's not divide them into the 2 that. So it is a paper about the covariance matrix, so by Roman and Misha and others. But I just wanted to let's look, for example, at the constraints at the middle panel on the left, constraints that you get on the dark energy equation of states, just to mention one of them. What would happen if you don't, when you do constraints on that parameter, if you only had to marginalize over cosmology? If you knew all of these other cosmological parameters, and nuisance parameters would be the lowest curve. If you just had to fit the cosmology, it would be the middle curve. And the red curve on the top is the effect of having to marginalize over all of these nuisance parameters. And you can see that, it's a very big effect. And I think everybody in cosmology sees these days and understands this. So it's a big deal. So how, on the plot on the right, it's just about some futuristic surveys and so on, to give you a sense of how well we are able to measure with these futuristic surveys those higher order parameters, this B2, B gamma 3. These are all more complicated bias parameters than the usual B1 that enter into this relation, and they are important if we wanted to get constraints that are not biased at the size of these small error bars. And you can see that the error bars with which you get those bias parameters from the data alone is around 10% or a few percent. So if you were somehow being able to know the size of these bias parameters to this from somewhere else, either from smaller scale observations or from a combination of modeling of the small scales and some understanding, that one could predict them better than 10% for a given sample, say once you've observed the linear bias or the number density of tracers, then you will start making progress and eating into these big error bars that you're getting from the marginalization. So, that's like kind of a target of what, so to get this precise calculation, you have a handful of parameters, each of which, if you knew them to better than 10%, then you wouldn't be paying such a big price. So that's kind of the target to have. This is very important for constraints on things that I've always been very interested about, like the non-Gaussianity of fluctuations, which are a nice window into the very early universe. If you didn't have to marginalize over these parameters, you would do so much better. You could easily convince yourself you could do better than Planck and future CMB experiments, but you're losing so much from this marginalization that it's difficult to compete. And it's again, one is looking for sub% effects there, and one needs to be able to convince yourself that you can make predictions for say the 3-point function of fluctuations that are at the sub% level without having to marginalize over so many parameters. It is true that when we do these calculations now, these free parameters enter, in specific ways in all of the endpoint functions, but still, after you marginalize over all of these, you pay a lot, and it's hard, especially for some of the types of non-Gaussianity that are quite degenerate with other effects. So in order to really make progress, you would need to be able to somehow predict these bias parameters to 10%, or these 3-point functions, say somehow from first principle to a fraction of a percent level, without having to margins, perhaps calibrating your model with some other type of observations, smaller scales that are not in here, or cross-correlating with other surveys. So that's the target, is to see if one can make predictions for these observables at the sub% level without having to marginalize over these nuisance parameters. I think it sounds tough, but probably not completely crazy. So to finish, let me say that, yeah, as I was saying from the beginning, there are many questions still in cosmology. We hope to get some of these answers from the clustering of large scales. On large scales, it's very simple. The dynamics is almost linear theory, but not quite. At the scales from what we're getting information, in these clustering surveys, the corrections are on the 10% level, so they are very they're very they're reasonable place to try to make some progress analytically. We've made quite a bit of progress. We understood a lot of things about these large-scale dynamics and how to make it accurate, and where the effects on the small scales are actually coming in, and how many parameters are needed in this. Or it's not that they are needed; they just are in your face. You cannot do this calculation without those free parameters. It's just it could give nonsensical results for other universes, and so it's not even self-consistent. So we understand all of that, but I think in addition to more progress into doing some higher order calculations they would still need, or covariance matrix and things like that, I think it's now time to try to make a connection with the smaller scales, to try to squeeze these errors that are coming from these small scales on the large scales. I'm hopeful that the progress can be made, but that's I think for the future. So let me stop there.
Thanks very much, Matias. I'll clap for everybody. Stephanie does at our Thursday talks. Are there questions for Matias? Can you use the raise hand feature in the chat? I think Sigurd actually typed out a question earlier. Sigurd, did you want to ask that now? Maybe he's not on.
I'm not sure how to see those chats.
No, it's several slides ago, and it wasn't very important. It was, yeah, we can skip it.
I have a question while other people are figuring out their questions. Matias, it was a wonderful talk. And the whole program is so beautiful. Can you give us some examples just to have a better intuition about the kind of things that you would, I'm trying to develop more of an intuition about the things that I understand abstractly, but that practically speaking, what kind of errors, let's say in a cosmological simulation, would induce uncertainties in these well, you're calling them nuisance parameters, but these parameters that characterize effective theory. Like, are we talking about galactic scale things and how feedback works, or sort of cluster scale things? And just give us a few physical examples, would you, of the sort of Like if you
Yeah.
changed something like that, how much would it change which nuisance parameters and so
Yeah.
on?
So in terms of so let me give two examples. One would be if we're talking about tracers like galaxies or something like that, where of course all the physics of galaxy formation and so on is much more important. Another one, if we were talking about just the distribution of matter, in the distribution of matter, even in the case of the dark matter alone, the fact that that dark matter particles on small scales are moving around, the nonlinear motions, it creates something that is similar, enters like similar to a viscosity type of parameter in a. If you were to write down a stress tensor from the small scales, it would look like
I understood that part.
Yeah.
I understood the conceptual level, how it arises. I'm trying to get an idea of the magnitude of that you could expect. Maybe you're going.
Well, the magnitude that you can expect is that you see suppressions of power of the size or terms that look like momentum k times some typical size motion, which is few megaparsecs, damping the power spectrum. So a correction to the linear power spectrum that would look like, or what you compute with linear theory, that would look like, for example, e to the minus k square, some distance square times the linear power spectrum, coming from diffusion, if you want, on the small scale. And of course, if you were tracking separately the dark matter and the baryons, these parameters would be different for each of them as a result, for example, of feedback and motions on small scales. So when you're doing calculation for, say, like that, if you're tracking baryons and dark matter, maybe you're interested in lensing or something like this, then you have to keep these separate. They're separate parameters for both of them, and the order of magnitude of this distance is that one. On the relationship between this calculation and the tracers, the abundance of tracers, these higher order biases, they are encoding what people maybe call the assembly bias, and so there's that's what they are encoding, but they or how the number density of galaxies depends on the large scale environment, but it tells you that to a given order to a given precision that you want, the way that this dependence enters into the calculation is, for example, through the linear bias is but some density square or the tidal fields, and there are a few other. There's a particular cubic combination of the derivatives of the density. That's the only one that is relevant to this order of the so you would need to know. You could, for example, run a simulation and compute this large scale cubic combination of the derivatives of the density, how this changes in the different parts of the box, and count how many galaxies of whatever the type you're interested in, how this is changing, correlated with that specific combination. This is, to this order, you just need more or less 3 of these parameters, these bias parameters. If you needed to go to a bit more precision, to one more loop, you need a few more. So, but it's a specific part. The dependence on the environment, at least in this way of doing it, cannot come in an arbitrary way, or you just don't care, other than the ways that the number density of galaxies correlates with this particular combination of derivatives of the density and velocity and so on. Because it needs to correlate with, go ahead.
in principle, if you had something that was kind of smooth like a neutrino mass, that you might be able to even compute the higher order corrections.
Yes, yes,
for-
yes. So for example, yeah, so that's I mean, I didn't include, but that's kind of an interesting example because yeah, so neutrinos, I mean, as a conceptual example, it's interesting because why does this perturbation theory work? It works because if you're interested on scales much larger than the scales of which things have been able to move, once you go on scales, so typical motions in dark matter structures, say, let's call it 10 megaparsec. If you're interested in scales much larger than that, then that's the expansion parameter. In the case of neutrinos, if you include them, okay, they're a small fraction, but some of those neutrinos are more relativistic than others. They can move much different, much larger distances. So naively, this perturbation theory or this EFT is breaking at a much larger distance. And so, but you can work around and do something. That's kind of, yeah, conceptually is very interesting. Now in practice, the neutrinos are small amount, are a small enough contribution that some of these conceptual things are not super, you know, they don't make such a big difference that you need to care about them. But being able to do the one loop computation for the neutrinos is not so easy. I mean, it's not. I mean, I found it an interesting exercise.
Okay. So we're a couple minutes over now, but I wanted to let Rachel ask a brief question. She had her hand up.
I don't know if it's brief, so maybe I'll just catch Matias another time, but thank you.
Okay. Yeah, I have a lot of questions for Matias also after this talk. So with that, why don't we all thank Matias again?
Thanks very much for inviting me.
Thank you for coming, and thanks everybody for joining the colloquium.